Okay, so last time we were talking about derivatives of parametric curves and velocity and acceleration and stuff like that. And we'd started in on this example where we're given a velocity, and from that we want to infer the acceleration, we want to infer the position. And we did the easy one first, which is if you know the velocity, well, acceleration is the derivative of velocity, and that's just a little bit of single variable calculus is no problem. So that's what we did last time. And I believe that's where we drew the line. So next step, how do you find position? Well, okay, you have to think this through. We already know velocity is the derivative of position. So that means position is the antiderivative of velocity, right? Just like in the Calc 1 context. So we're going to just take the antiderivative of the velocity that we were given right there. So a pretty straightforward calculation to find the antiderivative. You just do antiderivatives one component at a time. After all, we did derivatives one component at a time. So undoing that, still one component at a time. Easy calculus follows. The one little tricky bit is, of course, you get an integration constant. And now how to evaluate that integration constant? I want to point out the common misunderstanding, mistake, pretty catastrophic mistake that a lot of students will make is based on their high school experience. They believe that integration constants are always the same as your initial condition. And that is just not true. It just isn't. We're going to see in this example that it's going to absolutely not work out to be true, right? So anyway, let's walk through and see how this works out. What I can definitely do, let's see. In fact, I can. I can hit this button there. There, we've got more space. Okay, what we can definitely do is take this equation that has, if you will, kind of three terms in it, and we can just plug in t equals 0 into all three of these terms. Right? If this is true for all values of t, then it's true for that value of t. Right? So, okay, fine. Plugging in t equals 0. You plug in t equals 0, that becomes 5, 6. Let's see, you plug in t equals 0, and this business here, you got to plug some stuff in, right? But if you just plug in the numbers, you get 3, 1. And the constant that we're actually looking for, of course, is a constant, so it doesn't change when you set t to be some value. It's always the same. Okay. So that original purple equation becomes this purple equation. Is everybody on board? Easy to solve, of course, this new purple equation. This is C is just 2, 5, and notice it is not the initial value. All right, does everybody follow that argument? So let me tell you where I think the myth comes from. I think it's because of, let's see how to say this, too boring of a pattern of examples given in high school classes. Right? What they do is they always use polynomials for the function. And so if you think about it, if this here is always polynomials, then when you take the antiderivative, this is always going to be polynomials where there's always at least one factor of t. And you plug in t equals 0, and that always turns to 0. Now, again, that's not literally always true. You can see here, it's definitely not 0 here. But if every example you've ever seen has this turn into 0, then you can see how in those cases, you would get that C is equal to the initial condition. That would be the illusion that would be created by these narrow, weak examples. Does that make sense to everybody? So please don't step on that landmine, make that mistake. It's just, and you got to keep in mind, it's not about the answer, right? It's the problem here is not that you will get a wrong answer. The problem is that your reasoning will be invalid, right? And so therefore, even if you get lucky, even if it just happens to work out, doesn't matter. Your reasoning is still wrong. So make sure to actually do the plugging in. Don't just claim nonsensically that the integration constant's the initial condition. It isn't. Okay. All right. Now, super quick on this. I do want to point out that this is this is not an integral. A lot of people will look at this and say that's an integral. It's not. It's an antiderivative. Now, I know, and I know y'all know, that there's a very strong, powerful connection between antiderivatives and integrals. But they are really, really different things, certainly in how they're defined and certainly in, in certain contexts and how we use them. So it's important to make that distinction. This is an antiderivative. I'm literally taking the process of differentiation and saying I would like to undo that differentiation that turned x into v so that I can turn v back into x. Right? So an integral is a totally different thing. An integral is a Riemann sum, for one thing. An integral always gives you a value. That's not what this is. This is a function. Really different critter. Right? So now what I'm doing right now is just kind of laying a little bit of groundwork. I just want to persuade you that this is an important distinction. And if you're a little shaky on this, if you're not really quite sure you follow the distinctions I'm making between antiderivatives and integrals, then let me refer you to, I have a recording where I've kind of gotten this all off my chest, as it were, and put it into one video. It's on my miscellaneous topics playlist on the YouTube channel. And so if you want to hear, 20 minutes on this stuff, and maybe kind of polish up your understanding of integrals and antiderivatives and related notes. I hope you'll take a look at that video. Anyway, okay. All right. Last thing in this section, we're going to talk about one little bit from what I'll call the Kepler stuff in the rest of this section. So most of what's in the Kepler's analysis of planetary motion and that kind of thing is not part of this course. You'll notice on the content syllabus it is it's in the excluded material column, right? And you're not responsible for it. And I am a little sad about that because it is pretty cool math, right? And it is of historical importance even, right? It is a really cool stuff to talk about in there that we just don't have time to do. So we exclude it because we just don't have time, not because we don't want to. That said, there is one thing that you do need to know that you are responsible for, and that is this one theorem in there. It's no surprise. It's exactly what you would kind of hope, but we do need to use this here and there, and so it does need to be established. Notice that this is just about various products, dot product and cross product. What happens when you take the derivatives of these products? Now, they're not products of Calc 1-esque functions, right? These are products of vector-valued functions, dot and cross products of those vector-valued functions. Nevertheless, we're talking about derivatives of products. Therefore, these could reasonably be called product rules. You'll notice they look just like you would kind of hope, right? I mean, if you had to guess, right, naively without working it out, what these were going to work out to be, I think you'd probably guess these, right? And they do. They work. It's fine. So anyway, that just needs to get said. And all the rest of the stuff in the Kepler section you're not responsible for and look at only to the extent that you're curious. Okay, now on to chain rule, section 2.5. Let's see here. So there's a particular point of view that I want to start with the chain rule. There are many points of view that can be taken. I will show you more than one point of view, but I want to start with a very specific point of view because I think it's ultimately the most natural point of view, and it's ultimately, again, just to me at least, the one that's most intuitively satisfying. So, in order to do that specific point of view, I'm going to rewind momentarily and go back to single variable calculus just for a minute. Now, I know that y'all know the single variable chain rule. My purpose here is not to teach you the single variable chain rule that you already know. My purpose here is to set up a specific point of view on the single variable chain rule, because if we take that very specific point of view on the single variable chain rule, that'll make it easy to extend to an analogous point of view on the multivariable chain rule. So think of this as a segue. This is a setup for stuff that we're going to be doing in a minute. All right, so what is a derivative? Derivative is a lot of different things, right? Multiple interpretations. Here's the one that we're going to use here. A derivative is a factor. It's the factor that you multiply by input velocity to get output velocity. That's the point of view I want to take. Specifically, it's a factor. Now, yes, I could interpret it as a fraction, or I could interpret it as a slope, or I could interpret it as a rate. Yeah, fine. That's not what we're doing here, right? So for the moment, this is how we're going to think about derivatives. Derivatives are factors. Okay. All righty. So with that established, let's look at this scenario where I have a sort of a concatenation of two functions. You see here we have the function f that takes in x's and gives out y's, single variable function. Here is a function g that takes in the y's that came out of the first function and spits out z's. Right? So when you have two functions that kind of Lego fit together like this, the one goes into the other one, you can talk about the composition. The composition of these two functions takes in x's and spits out z's. So there are three functions on the screen here. We have f, we have g, and we have their composition. Is that cool? Is everybody good with that? All right, now I'm going to take the point of view that we have above on each of these functions. What is the derivative of f? Well, the derivative of f is the factor. It's what I multiply by x prime to get y prime. That's what the derivative of f is. It's that multiplicative factor. Okay, let's talk about what is the derivative of g. Well, the derivative of g, color mistake. The derivative of g is this factor that I multiply by my input velocity to get my colors. To get my output velocity. Again, it's just a factor. Is that, same idea applied now to the second function in the sequence. And then let's talk about the derivative of the composition. Well, same story. The derivative of the composition is the factor that I multiply by x prime to get z prime. Yeah, question. Oh, I'm sorry. I thought that was, okay. Yeah. Okay. All right. So,
That could be a silly question, but is there a reason why we're marking them as prime? Because I've seen that also used to say derivative.
I literally mean derivative here, yeah. So I'm viewing everything as depending on time here. And so this input point, which you might call x, is moving. Right? And so imagine a particle that's kind of moving along the x-axis here. And so x prime, I literally mean the time derivative, dx dt, yeah. But I want to focus on thinking of the derivatives of these f, g, and the composition as being the derivatives in question. So I wrote prime just to kind of avoid, I mean, yeah, they are derivatives, but I want to think of them as being velocities. Is that cool? Yeah. Okay. Right. Okay, cool. All right, so now let's just think out loud on an intuitive level and forget about the equations for a moment. In the process of turning x prime into z prime, I mean, that's what the derivative of the composition does. It turns x prime into z prime. But in that process, notice what I've done is I've multiplied by a factor, which is f prime, right? And then after that, I multiplied by a second factor, which is g prime. So altogether, what do you do to x prime to produce z prime? Well, you multiply by the derivative of f, and then you subsequently multiply by the derivative of g. And altogether, you've multiplied by their product. You've multiplied by g prime times f prime. So that's the chain rule, single variable chain rule. Let's see here, let me do it like this. We multiplied first by f prime, and then we multiplied by g prime. Altogether, that is how we turned x prime into z prime. Is that cool? All right. Now, if you want to follow the algebra on this page, go ahead. I mean, it's really just kind of formalizing what I think is better understood in sort of intuitively as, look, you multiplied by a factor, you multiplied by a second factor. Altogether, you've multiplied by a product of those factors. Right? But if you do want to follow the algebra, the way to see it is that this formula for y prime, if you plug it into there, gives you this. Feel free to follow the algebra at your leisure. And then if you compare this equation with that equation, then notice that means that this thing here has to equal to that thing there, which is our result. That's just the algebra. Don't get lost in the notation and stuff like that. Okay, so now punchline. Theorem you already know, and that I know you already know, right? So again, the point here is not to learn the single variable chain rule. I know you already knew that. The point is to think about this point of view, that it results from thinking about how a succession of factors altogether is a product of factors. That's all that we're arguing here. And with all of that in mind, we're now going to, real quick, I guess I'll point out the pithy summary here. We looked at a composition, and the derivative of that composition is the product of the two individual derivatives. So you can think of it as differentiation turns compositions into products. That's just convenient language. It's not a critical point. Okay, all right. So with this perspective in mind, a succession, a sequence of two functions gives a composition, gives a product of factors. Let's do the same thing now in a multivariable context. Now, again, there's a bunch of different ways to think about multivariable derivatives. They're all good. I like them, right? Great, but we're going to take a narrow, specific, highly analogous point of view so that we can try to rip off the work that we just did and kind of make use of it in this new context. And it is as follows. Just like on the previous page, a derivative is a factor. It's what you multiply by input velocity to get output velocity. Now, this is different. In this case, we're talking about an input velocity that is a vector, not a scalar. And we're talking about an output velocity that is a vector, not a scalar. And we're talking about a factor that I multiply by one to get the other, that factor being a matrix, not a scalar. Right? So these are different objects. They're vectors and matrices, not scalars, but strategically, structurally, notice it's really the kind of the morally equivalent same idea that we were using over here. Is that cool? Right? So here the derivative is a scalar factor that you multiply by scalar input to get scalar output velocities. Here, a derivative is a matrix factor that you multiply by vector input velocity to get vector output velocity. Okay, totally analogous. Now with that in mind, again, here is a sequence of two functions. Notice that we have first here a function that takes in the x variables and gets out the y variables, followed by a second function that takes in those y variables and spits out the z variables. And again, I can talk about their composition. Composition that takes in the x's and kind of does the whole two-step process, resulting in spitting out the z's. So again, three functions. And again, we can just write down exactly what the derivatives do, just, using this idea here. Derivatives are factors. They're matrix factors that multiply by velocities to give other velocities. You might think of it as it's what you multiply by this to produce that. That's what a derivative is. So, okay, looking at this picture here, the derivative of f is what you multiply by that to get that. The derivative of g is what you multiply by that to get that. So altogether, if I want to think about the composition where I start with x's and I end all the way over here with the z's, if I want to turn my x velocity, x prime, into my z velocity, z prime, well, what's going to do that? Well, I multiply by this factor called df, and then after that I multiply by this other factor called dg. Altogether, I'm multiplied by product of two separate matrices, df and then dg. And let's see, let me get this all on the screen here. Here we go. So df followed by dg. And that's what altogether turns my x prime into my z prime. That altogether then is the derivative of the composition. And notice, question.
So, what exactly is the middle y prime?
The middle what now?
Like the y prime.
Yeah. Okay. So we have this point here a. That's a constant. It just sits there, right? And when you plug it into f, you get this point f of a, and when you plug that into g, you get this point g of f of a, right? So those points just sit there. But I'm imagining that you also have on this picture, you have a point like a particle that's actually moving, where at the moment we're interested in, at that instant, it's at this point a, but it's moving with some velocity. Right? Remember, the idea of a derivative is that if you have an input velocity, in other words, if x is actually moving with some velocity, then that will cause its image to move also. So the idea is if my point over here is moving with velocity x prime, then there will be some, I don't know what it is, but there will be some corresponding y prime talking about how its image is moving, and that movement will cause some movement over here. Again, I don't know what it is, but we'll call that z prime.
What do you mean by its image?
Image means what comes out of the function. Yeah, so remember, this is terminology we talked about back in this was section 2.1. Remember, there was 2 pages where there's a ton of terminology that we had to set up, and that's just one of those terms. Image means what comes out of the function when you plug something in. Yeah. Okay. All right. Okay, so notice our multivariable chain rule. Not only do I get a formula that's morally doesn't this look a lot like what we saw on the previous page? Derivative of the composition is the product of the derivatives. Again, differentiation turns a composition into a product. Not only is it an analogous result, just matrices instead of scalars, but it's an analogous argument where you think of the derivatives as being factors, and then the combined factor is just the product of the individual factors. And that's really kind of all there is to it. All right. Okay, now there's some little specific little particulars that can make this confusing, and students can get backwards or get wrong in various different ways. So before we do an example, I want to address these little annoyances. This picture that I've drawn here, you'll notice that's two-dimensional, that's two-dimensional, that's two-dimensional, and it's tempting to say, okay, well, we seem to only have a result that, we've only entertained it in 2 dimensions, and so I guess our result only works in 2 dimensions. And that's just absolutely not true. That's just the picture I happen to draw. But notice that two-dimensionality of these pictures doesn't manifest itself at all in the algebra, right? This equation here is true for how we turn input velocities into output velocities, no matter what the dimensions are. So the dimensions can be whatever you want. It could be 2 to 2 to 2, like this, or it could be 6 to 2 to 4, whatever. These matrices will then have different shapes, right? But those shapes will fit together with matrix multiplication exactly as they should, because, of course, they are relating all the same trio of vectors. So don't worry about the dimension. It works however you do the dimensions. Second thing, and this is a frustration, and I'm sorry about this. This used to really bother me. Notice in my sequence of functions here, f is on the left and g is on the right. But when I write the composition, g is on the left and f is on the right. And that's easy to mess up because it's inconsistent. So heads up about that. Now, why is this? And who's the jerk that decided to write the composition this way, G compose F? Well, I get the sentiment, right? It does seem backwards. But notice the way we compute G compose F is, if you have G compose F applied to some vector x, the definition of that is it is G of F of x. And notice that F acts first and G acts second. So this is all actually consistent in terms of what's first and what's second. It's just different in terms of how it lays out on the page. So now again, very frustrating that this and this are out of order and, not happy. But wouldn't it be even worse if these were out of order? Right? I think that'd be even worse. So there's just no getting around it. Because of the way we write functions act on the left of what they're applying to, and as a result, subsequent functions act further to the left. We've painted ourselves into a corner here just with how, hundreds of years ago, how they decided to write function notation. And a case could be made, strong case could be made that wouldn't it be nice if the function were on the right instead of on the left. But anyway, this is where we're at, and there's nothing we can do about it. So heads up, be careful about the order. Be careful about, don't conflate left and right with first and second. It depends on which, are you looking in the algebra, are you looking on the diagram? And you got to make sure to keep that straight. Yeah.
If I were solving these as matrices that I'm multiplying, I'm working right to left.
I'm not sure what right to left means. The chain rule is that whichever one acts first is on the right. Is that what you meant?
Yeah.
Yeah. Whichever one acts first is on the right in the chain rule, and whichever one acts second is on the left in the chain rule. Yeah. Yeah. But think of it this way. Here's my suggested way of thinking is that whichever one is first in this notation. It's also first in this notation. It's also first in this notation. It's just that where first is different depending on what kinds of notation we're talking about. So be super careful. Okay, last little comment that I have to throw out there is a lot of students find themselves confused about this business right here. Why is DG evaluated not at A? DG is evaluated at F of A. Why? Right? That seems very weird. Okay, let me work my way up to that. I'm going to start off by reminding you that DF turns this velocity into that velocity. DF is a matrix consisting of a bunch of partials. It's all partials of functions of the x variables with respect to the x variables, evaluated, therefore, at the point where you are in the x space. Right? So the reason that this derivative matrix is evaluated at this point A is because, well, that's where we are when we're applying that matrix. We're at that point A pretty literally. Okay, now with that in mind, let's think through the analogous thought for the DG matrix. And the DG matrix turns this vector into that vector. The DG matrix consists of a bunch of partial derivatives of functions of y1 and y2 with respect to y1 and y2 when we are at a certain point in the y1, y2 plane. So when we are writing down DG, this is where we are. We are at this point, f of A. We are not at the point A. We are nowhere near the point A. A doesn't even live in the same universe as where we are when we're talking about the DG matrix. The DG matrix is defined over here in Y world. Again, it's never heard of X world. So this is just what it has to be. It's not like this is a tweak of what it should be. This is literally the only thing that it could be. Does that make sense to everybody? Is everybody all right with that? Okay. All right, so don't forget about that little annoyance. All righty, moving along. First example. Okay, good. We got plenty of time. So we have some functions given, not formulas, right? The formulas here aren't given, but in addition to being given these variables related by these functions f and g, we're also given certain data about the values and derivatives of these functions. So that's all given as well. And with all of that set and given, we want to compute this derivative matrix and this partial. Okay, does everybody see the question? We'll come back to the partial business. For the moment, let's talk about the derivative matrix. Step one, we write down the chain rule. Boom. The chain rule just tells us exactly what we're going to need. I'm going to need the derivative matrix of the first function, f, acting first, which means on the right. Right? You gotta make sure to get that right. It's easy to get those two matrices backwards, and that's really, really importantly wrong. So derivative matrix of f on the right, derivative matrix of g on the left, derivative matrix of g, of course, evaluated not at my point 1, 2, but at my point f. of 1 comma 2. All right. Now, how am I going to find these derivative matrices? Normally, I would take my formulas and take various partials and just, generate them. I have no formulas. Can't take any partials. So we have to hope that we might happen to have been given what we need. And lucky break, look at this. That is exactly one of the things that we're already given. So, sweet. That's just a matter of recopying there. Okay, the next factor, second factor, we're going to look at this DG matrix. I need DG evaluated at f of 1, 2. I have DG evaluated at, 3, 1, 0. Those don't look immediately, obviously, be the same. So the good news, of course, you can probably see this, is that the f of 1, 2, where I need this to be evaluated, actually is 3, 1, 0. So lucky break, even though cosmetically at a glance it doesn't look like it's what I need, it actually conveniently is exactly what I need, and therefore that goes there. Everybody all right? Okay. All right. And then everything, the rest of this is just arithmetic. You all know how to multiply matrices. I do want to point out there is something about the statement of the question that could be taken, depending on your point of view, to be a tricky aspect of the question. I'm going to suggest that this is actually not a trick question. To me, a trick question is a question that turns critically on some sort of little triviality that the question deliberately sweeps under the rug that isn't really the point of the question. That's not what happened here. This turns very importantly on something that really is very important conceptual idea, fundamental to how the question works. And specifically, notice that I gave you f and its derivative, and I wrote them on the left, just in the statement of the question. But in terms of how they show up in the algebra, they're on the right. And I gave you G and its derivative matrix on the right in the statement of the question, but it needs to be on the left in the algebra, right? So, again, you could, if you really want to take that point of view, you could say, oh, well, that was a trick question. It's not. It's important, right? So you cannot just assume that the matrices should go in whatever order they happen to be given to you. That's certainly not going to be the way it's going to be in your engineering futures or, math or physics or whatever. You've got to look at the context and think it through and decide and realize, wait a minute, which one is first, which one's second, and what does that mean about which order they should be in, independent of how the question happens to have been presented. Does that make sense? So please view that as an important part of a responsible application of the relevant ideas, and not as a trick. Everybody on board with that? All right. Okay. Okay, now we've done half the question. The question was to find the derivative matrix. There it is. Next part of the question, though, is to find this partial. Notice that is a partial of one of the output variables, Z3, right, with respect to one of the initial input variables. I lost my track as I was drawing the x1. Okay, so the first initial input variables, right? So one of the eventual outputs, partial with respect to one of the initial inputs, this is a partial derivative of the composition. That means it's going to be inside of the derivative matrix of the composition. But which one of those elements is it? Okay, so here's the big idea. Notice that We're taking the partial with respect to x1. x1 is the first input variable, so we look in the first column. Notice further, we are taking the partial of z3. That is the third output variable. That means we're looking in the third row. And so this number is the partial derivative we're looking for. How we doing on that? Everybody all right there? Okay. Cool. Okay, some special cases that I want to talk about here now. These special cases aren't going to tell us anything we don't already know. I have entertained putting the examples that will follow momentarily actually back into section 2.3's notes, because the conclusions we're about to come to are conclusions that we already knew back in section 2.3. We're not about to learn anything here, other than it's just kind of neat how things that we thought of previously from one point of view could alternatively be thought of from a different point of view. Special cases of the chain rule, as it turns out. So here we go, starting with what happens if you have one and only one input variable. And how does that, what does the chain rule turn into in that case? Well, you can just write out the chain rule here for this sort of sequence of functions. Here's what the chain rule turns into. Note specifically that if we look at this first function, that first function only has one input variable. Input variables correspond to columns. That means its derivative matrix is going to have only the one column. But furthermore, when you have a function that gives, notice, position as a function of time, that's a parametric curve. And we already know that the derivative of a parametric curve is a velocity vector. So really, it's kind of neat how this turns out. The chain rule, in this special case, when you have just the one input variable, the rightmost matrix is the velocity of a parametric curve. And furthermore, look at the composition. The composition, again, we have position as a function of one variable. One variable means the derivative matrix only has the one column. And being as this is a parametric curve, we're looking here at the derivative of a parametric curve. This too is a velocity of that parametric curve in the y space. So the way I like to think about this then is what we have here is this represents a velocity vector in our Rn space, and this represents a velocity vector in our Rm space. And so what we recover, again, something we already knew, but the derivative matrix of f, again, old news. We already knew this. The derivative matrix of f just is what's the factor. You multiply by input velocities to get output velocities. Old news. And so the only thing that's new here is that you can think of this, what previously we would have called just an interpretation of the derivative matrix. Now we can view as a special case of the chain rule. So now again, this example, there's nothing about this example that wouldn't fit just fine and dandy into section 2.3. This is literally using the ideas from section 2.3. It's perfectly reasonable. And notice there's a bunch of little particulars about particles and movement and velocities and whatever. But we have apparently an input velocity, and we are asked to compute here an output velocity, and we're going to do so with the derivative matrix. Just directly applying those old 2.3 ideas that we're now reinterpreting as a special case of the chain rule. So, yeah, you do have to take your function, take the appropriate derivatives, plug in the appropriate value of a to get the actual numbers. Yeah, so a little bit of mechanics, a little bit of algebra, a little bit of arithmetic. But big picture-wise, this is just using that old interpretation of derivative matrices. What do you think? Everybody all right? All right, special case of the special case. So again, a single input variable. Here, let me do it like this. A single input variable again. Oh, gosh. Oh, come on. Again, let's call it t. This time, the special case of the special case is we're going to consider what happens when you have also just a single output variable. All right, so again, looking at the three different functions, again, there's the first function, there's the second function, there's the composition. Looking at those three different functions, the fact that we have one initial input tells me that I have only one column in each of these matrices. The fact that I have only one output means that I have one row in each of these two matrices, which means that all together, and again, you can see this right here in the diagram, notice that the composition itself has one variable in and one variable out. This composition is a good old-fashioned Calc 1 single variable real valued function. And its derivative matrix is literally just the one derivative. So in this special case of the special case, again, it's just a chain rule. The derivative matrix for the composition is the product of the derivative matrices of the individual functions that make up the composition. Nothing's really different there. It's just that this is what it looks like when, again, you have just the one in and just the one out. The one other observation I'll make about this, because it's kind of a nice little optional point. Keep in mind this is a derivative matrix. This up here says matrix times, matrix vector multiplication times this velocity vector. Sure, but when you have a single row, as we do in this case, one output variable, one row, matrix vector multiplication is effectively a vector dot product. And this, again, is just kind of an old fact from linear algebra, that if you have a vector transpose multiplied by another vector, this is a matrix vector product. And if you compare that with the original vector dotted with the other vector, these are the same. It's all the same arithmetic, this times that plus that times that plus, it's all the exact same terms. You can view it as a matrix vector product. You can view it as a vector dot product. Doesn't matter. Okay. So said differently, in this scenario where you have one initial input and one eventual output, dot product with the gradient is an alternative point of view that you can take on how to turn input velocities into output velocities. So again, example. Again, this example is not news. There we go. This example would totally work, no problem, in section 2.3, and I'm actually literally copying it into the 2.3 notes. But notice we have exactly that scenario. We have a bird that's moving. The bird moving means that I have position as a function of time. And then there's also this temperature function, and the temperature function gives me temperature as a function of location. And sure enough, one initial input variable, time, one eventual output variable, temperature. And so if you want to know the derivative of this composition, temperature thought of as a function of time, and how does temperature vary with time? It's just a chain rule problem. The chain rule in this case can be written like this. And so again, it's just a matter of dotting with the gradient vector, and then algebra ensues. You got to take the appropriate partial derivatives to get the gradient, plug in the appropriate point, arithmetic, all that. That's just details. The big picture is we're just dotting with the gradient. Everybody good? Okay, and I think I see from the clock over there that we are out of time. Oh, yes, we are. Okay, calling it there. See you on Friday. And don't forget we have an exam on Friday. So, usual time, usual location. See you then. Good luck with your studying.
Thank you very much.
Yeah.